Today we will be continuing with the discussion on penalty approach, and then we will see what are called as multi-point boundary conditions. So far we have only seen single point boundary conditions, that is constraints of the type qi equal to ai, or let us say q1 is equal to a1, and we have seen that if we have a constraint of the type q1 equal to a1, then using the penalty approach we get this as a system of equations where k prime is the stiffness matrix obtained by adding a term c to the diagonal element of location 1, okay, and this is a k prime matrix. The q matrix remains the same, and the f matrix, that is f prime, is obtained by taking the global force matrix and adding to the first location c times a1, okay, where c is some large number. Now in this system of equations, the first question is how do we decide the value of c? Just saying that c is some large number is not sufficient, okay, because when we have to solve it algorithmically, we need some way of estimating the value of c. If you notice, this parameter c is appearing only in the first equation. That means this row multiplied with this column is equal to this term. That is the only place where this value c is coming. Okay, c is not appearing anywhere else in the equations. So if I just write down this equation, the expression would be k11 plus c times q1 okay. Now in this system of equation, or in the given system of equations, this is the only equation which has a parameter c. So if I say that my c should be larger than k1, k1, k11, k12, k1n, all these coefficients, and larger than all these coefficients by an order of magnitude. So we can say that c, we will take that to be equal to maximum of k11, k12, so on till k1n, and we will take the maximum and multiply that by some order of magnitude, let us say 10 to the power 4 or 10 to the power 5, something like that. Okay, we will take the highest of all these coefficients and multiply that by 10 to the power 4 or 10 to the power 5, 10 to the power 6, some large number like that, and that will give us a value of c. Okay, we know that the larger we take the value of c, the closer will be our the more correct our result will be, because we finally want that q1 should be equal to a1. Okay, so if we take a very large value of c here, we will finally get this q1 to be equal to a1. Okay, and how do we show that? Earlier as I mentioned that US, that is the strain energy in the spring, is equal to half of c times q1 minus a1 squared. Okay, the total strain, the total potential energy system in the system was pi, which is equal to US plus the other terms, that is half of q transpose kq minus q transpose f. Okay. Now in this potential energy expression, we are trying to minimize the potential energy, and when we are trying to minimize the potential energy, this will be minimum only when this term becomes very small. Okay, if c is large and q1 minus a1 is not equal to 0, this term will become very large. Okay, so only when q1 tends to be equal to 0, we will be able to minimize the potential energy. Okay, so if we take a very large value of c, in this system of equation we will finally approach towards the condition of q1 equal to a1, and for taking a large value of c, we can normally take a condition of this type. This we can change, this factor instead of 10 to the power 4 we can change, take it any factor, but c should be larger than all these coefficients and larger by an order of magnitude. Okay. Let us take a small example for this penalty approach. and then maybe it will become clearer. The same example that we had earlier. This is a force of 100 pounds, this distance is 12 inches, the lower distance is also 12 inches, and this we had approximated by two elements of this type. Okay, the area of cross section for this was, if I remember correctly, 5.25 square inches. The area of cross section for this was 3.75 square inches. Okay, and the global matrices that we had, they looked something like this. The global stiffness matrix was 1.31 minus 1.31 0 minus 1.31, this is 1.31 plus 0.94, this term is minus 0.94, this is 0 minus 0.94, this is 0, this into I think 10 to the power 7. This was the global stiffness matrix, and the global force matrix, that was 5.25 into 0.28 into 6, this is 9 into 0.28 into 6 plus 100, and the third term was 3.75 into 0.28 into 6, the transpose of 4. This is the global force matrix. Okay. Now, if I use the penalty approach, then I have to modify both the K matrix as well as the F matrix by adding the C terms. Okay. So, let us say I take C to be equal to some value, let us say 1000. Okay, and my boundary condition in this case is Q1 is equal to 0. Okay, so if I take C to be 1000, I have to modify my K matrix by adding 1000 to the location 1 1. So here I will add, this will become plus 1000, and in the F matrix in the first location I have to add this plus C times A1. Again A1 is equal to 0. Okay, A1 is this term and C is this. Okay, so my modified matrices would become something like this. K prime would be, I have added 1000 into 10 to the power 7. So this will become 1000 1.31 minus 1.31 0 1.31 okay, and a modified force matrix F prime, that would be the same as F in this case, because A1 is equal to 0. Okay, my system of equations would be K prime Q equal to F prime. Again, K prime is a 3 by 3 matrix, Q is having 3 variables, F prime is having 3 locations. I can solve this system of equations to get the value of Q. Okay, it's a simple set of linear equations, I can easily solve it out. Okay. So this is how we can use the penalty approach for solving single point boundary conditions. These are the single point boundary conditions because these are giving constraints on only one node at a time. Q1 is a deformation of one node. Okay, this constraint is giving a deformation of only one node, or is controlling a deformation of only one node. So we call them single point boundary conditions. Okay. In contrast to this, we will now see what are referred to as multi-point boundary conditions. Multi-point boundary conditions. Okay. In multi-point boundary conditions, we will basically take, let us say if we have any general element like this, we take two nodes on this, let us say one node here and another node here. Okay, let us say this is Qi and this is Qj, and we say that Qi and Qj will be related linearly. Okay, that means if I just say some constant C1 times Q1 or Qi plus some constant C2 times Qj plus another constant C3 will be equal to 0. Okay, that means the deformation of these two nodes is constrained in a linear manner. Okay, and typically situations where these kind of boundary conditions are used, let us say if you are talking of a situation like this, if we have a system like this where there is a lever which is tied by two ropes, and we assume that this lever is, let us say, very compared to the ropes. Okay, the lever is hinged at one end and we are applying some load at the other end. Okay, so then Qi and Qj, they have to be related in a linear manner. Okay, that means let us say if this distance is a and this distance is b, we will get a relationship of the type that Qi by a will be equal to Qj divided by a plus b. Okay, so this is a constraint which is relating to displacements Qi and Qj, and this is what we refer to as a multi-point boundary condition. And so far we have handled boundary conditions of the type Qi is equal to ai. Okay, we know we can use the penalty approach or the elimination method to solve problems with these type of boundary conditions. But if we have a boundary condition of this type, the same method will not be sufficient. Okay, or we will have to modify that method slightly to see how we can solve constraints of this type. Okay, another situation where multi-point boundary conditions are needed, or let us say if we have a circular cylinder, a uniform thickness, okay, and that is having internal pressure. In this case, since I am assuming a uniform thickness and the pressure is also uniform, if I have nodes here like this, the nodes are all going to move radially outwards. Okay, so this node will get deflected maybe to this position and this position respectively. Okay, but all these nodes should be moving radially outwards. Okay, now if I take just a section of this cylinder, okay, and I model my body just, let us say, only a quarter of the body like this, and I have one node here, another node here. Okay, this is Qi, this is Qj, this is let us say a deformation in the y direction. Okay, let us say deformation in the x direction are Qk and here they are, let us say, Ql. Now Qi and Qk, they have to be related to one another. Okay, because any point here will be moving in a direction at an angle theta. Okay, so the relationship between Qi and Qk will be of the form that Qi by Qk will be equal to probably tan theta or something like that. Okay, so again this is a multi-point boundary condition. Okay, because you are basically saying that a node here has to move only in the radial direction. That means the x direction deformation and the y direction deformation, they have to be related to one another. This is a two-dimensional case. This is not a one-dimensional case. Okay, so this is also a multi-point boundary condition. Okay, similarly, there are a number of situations where deformations of more than one node are constrained together by a linear relationship between them. Okay, so if you have a multi-point boundary condition, let's say if you take a general multi-point boundary condition, beta 1 QP1 plus beta 2 QP2 is equal to beta naught, where beta 1, beta 2 and beta naught, they are constants, and QP1 and QP2 are the deformation of two nodes. Okay, QP1 is the deformation of the node number P1, QP2 is the deformation of node number P2. Okay, if you have a boundary condition of this type, we will rewrite it like this: beta 1 QP1 plus beta 2 QP2 minus beta naught is equal to 0. Okay, and again we will use the penalty approach. Now potential energy expression pi is given by half of Q transpose K Q minus Q transpose F. Okay, that means if you have any general system, for this system this is a potential energy expression. Now we want to give it a boundary condition of this type. Now let us first see simply by analogy. Earlier we had a boundary condition of the type Q1 minus A1 equal to 0. So the penalty that we gave, that penalty was of the type half of C times Q1 minus A1 whole squared. This is the penalty we had given to the potential energy. Okay, if you this potential energy of the spring, half of C into Q1 minus A1 whole squared. This is the penalty we had given to the potential energy expression. Okay. Now we will do a similar thing over here. We have this is equal to 0. Okay, so we will give a penalty which would be given by half of C into this whole thing, beta 1 QP1 plus beta 2 QP2 minus beta naught whole squared. This is a potential energy penalty that we will give to this potential energy expression. Okay, so we will get pi to be equal to this plus half of Q transpose KQ minus Q transpose F. Okay, so with this penalty our total potential energy of the system would become this. Okay, and if this is a potential energy expression, we will again use the condition that we had earlier, that del pi by del Qi will be equal to 0 for minimizing the potential energy. Okay, so we will use these constraints and get a system of equations from this potential energy expression. Okay, let us quickly go through that exercise. Now this expression, potential energy expression pi is half of C times Okay, right now let's take Q P1. I will take this expression to be beta 1 Q1 plus beta 2 Q2 minus beta naught equal to 0. Okay, so P1 P2 I am taking Q1 and Q2 directly just for having simpler expressions. Okay, so this Q P1 I will replace that by Q1 and Q P2 I will replace that by Q2. Okay, so this will be half of C times Q1 beta 1 plus Q2 beta 2 minus beta naught whole squared plus we have half of Q transpose KQ. Again we will write the complete expression, that is half of, we will get Q1 K11 Q1 plus Q1 K12 Q2 Okay, this expression, this part of the expression is the same as what we had earlier. The only thing that we have now is we have a different term for the penalty. Okay, this is the penalty we have in this case. If I take this expression and try to evaluate del pi by del Q1, I am differentiating my potential energy with respect to Q1. If I differentiate with respect to Q1, I will get 2 times this thing, this term, and from a column I will get this term, so on till this term. And if I differentiate this whole thing, I will get C into 2, this whole expression multiplied by beta 1. Okay, so if I write that down, I will get C times beta 1 squared into Q1 plus C times beta 1 beta 2 into Q2 minus C times beta naught beta 1. This is what I am getting from this. 2 times this whole thing multiplied by beta 1. So 2 into and half will cancel, C into Q1 into beta 1 squared plus C into beta 1 into beta 2 into Q2, that is this term, and so on. This is what I will get from this expression. Okay, plus the term that I will be getting from these expressions would be the same as what I had earlier. Okay, there will be no change in those terms. Okay, they will just be the similar the term that we had earlier. There will be absolutely no change. And from here also, okay, I will get a term of minus F1. Okay, the last term here would be minus F1, and this whole thing has to be equal to 0 because del pi by del Q1 has to be 0. Okay, similarly, if I take del pi by del Q2, if I differentiate this with respect to Q2, I will get this whole thing multiplied by beta 2. Okay, that will give me C times beta 1 beta 2 Q1 plus C times beta 2 squared Q2 minus C times beta naught beta 2. and the rest of the terms from this would be the same as the terms coming from this column and this row. Okay, and this thing finally I will get minus f2 will be equal to 0. And differentiate with respect to q3. Differentiating this with respect to q3 will not give me anything, but when I differentiate the rest of it, I will get terms from the third column and the third row, and all these would be the same as what we had earlier. Okay, so all the other derivatives will remain the same. The only change would be in the differential with respect to q1 and with respect to q2. Okay, and if you look up these terms, these two are constant and I can combine them with the first terms. Okay, this term will get added to the coefficient of q1, this term will get added to the coefficient of q2. Okay, similarly in this equation, this term will get added to the coefficient of q1 and this will get added to the coefficient of q2. Okay, so if I write down this complete equation or complete set of equations in a matrix form, this whole thing will be equal to, I will write the first terms here, okay, the coefficient of q1 in the first equation has got this extra term of c beta 1 square. Okay, so here I will add c times beta 1 squared. Okay, the coefficient of q2 has got c beta 1 beta 2. So here I will add this plus c times beta 1 beta 2. Okay, similarly if I take up the second equation, coefficient of q1 has got c times beta 1 beta 2. So I will add this plus c times beta 1 beta 2, and the coefficient of q2 has got c beta 2 square. So this plus c times beta 2 squared. Okay, and the first terms f1 will, to f1 I will be adding c beta naught beta 1. Okay, it will become f1 plus c times beta naught beta 1, and the second equation I will add c times beta naught beta 2. So it will become f2 plus c times beta naught beta 2. Okay, so this complete set of equations would become equation of the type k prime q equal to f prime. But the difference is that now when I am evaluating k prime, I will have to evaluate k prime by adding these terms in the locations corresponding to q1 and q2. Okay, in the first row diagonal element I will add c beta 1 square. In the location 1 2 I will add c beta 1 beta 2. In location 2 1 I will add c beta 1 beta 2, and in the diagonal element for second row I will add c beta 2 square. And similarly I will modify the first terms by these expressions, and then I can solve for the system of equations. Okay. Any questions up to this point? Okay. So now we know how to solve for single point as well as multi-point boundary conditions. But one thing that we have not seen so far is that, let's say if we have any finite element problem with some boundary conditions, in order to constrain this body at this boundary, some forces have to be applied from the boundary. Okay, for instance, when we are talking of the simple case, in this case we mentioned that Q1 is equal to 0. Okay, but in order to get Q1 equal to 0, there will be some reaction from here. Okay, when we made the force matrix for this body, we had this is, let's say, node 1, this was node 2 and this was node 3. We have 3 terms, F1, F2 and F3. In none of these 3 terms have we taken into account this reaction. Okay, but this reaction is also an external force acting on this body. Okay, similarly when you are talking of multi-point boundary conditions, okay, some node here and some node here, they are constrained together. It's possible that there will be some reactions at these 2 points, as a result of which the deformation of these 2 nodes will be constrained in some manner. Okay, we haven't yet seen any way of finding out the value of these reactions. Okay, so let's see how do we evaluate these reactions. The other one-dimensional case that I had taken, if I consider this rope and this rope, I am considering this body, this rod to be infinitely stiff. Okay, if I consider this rope and this rope, there will be some reaction at this point. Okay, the rod will tend to pull the ropes down. We haven't yet evaluated those reactions. Okay, so whenever we are talking of any kind of boundary conditions, there will be some reactions at each of the nodes. Okay, let's see how do we get the value of these reactions. Okay, let's first see the simple single point boundary condition. If I consider this single point boundary condition, this system of equations, the first equation is this row multiplied with this column giving us this term. Okay, which I can write down as Q1 multiplied by K11 plus C plus Q2 K12 so on till Qn K1n is equal to F plus C times A1. Okay. In contrast to this, if you look at, so just look at the potential energy expression that we had earlier, half of Q transpose KQ minus Q transpose F, and I differentiate this with respect to with respect to Q1. Okay, the first equation that I will get will be, if I put this, the first equation would be Q1 K11 plus Q2 K12 Qn K1n will be equal to F. Okay, and on the node 1 we are saying that there will be some reaction. So the actual force acting here will be the other external forces plus the reaction force. Okay, so if I compare these two, what I will get will be that this reaction force at the node 1 will be equal to C times A1 minus Q1. Is that okay? Okay, C times A1 minus Q1, and if you remember our formulation, at this node Q1 we had added a spring like this, okay, and we said that this end will be given a deflection of A1. As a result of that, this spring will have a deflection of Q1 minus A1. So this force, the force in the spring, will be equal to C, which is the stiffness of the spring, multiplied by Q1 minus A1. Okay, the force of the spring will be equal to the reaction in magnitude. Okay, if you consider this node at this point, whatever the reaction you are having from here, that will be equal to the force in the spring. Okay, which is exactly what this relationship is telling us. Or if you just consider the magnitude, you can say C times Q1 minus A1. Okay, so the reaction would be C times Q1 minus A1, that is for single point boundary conditions of the type Q1 is equal to A1, and when we are using the penalty approach. Okay, similarly, if we consider multi point boundary conditions, okay, if you consider this system of equations, the reaction force at from this first equation that you will get, that I just write it here itself, R1, that will be equal to these three terms put together, okay, which will be C times, I will have to take this to the right hand side, so C times beta naught beta 1 minus C times beta 1 squared times Q1 minus C times beta 1 beta 2 times Q2, and similarly the reaction at the node 2 would be C times beta naught beta 2 minus C times beta 1 beta 2 Q1 minus C times beta 2 squared Q2. This would be a reaction at the second node, this would be the reaction at the first node. Okay, because the rest, these terms will remain unchanged. These three, if I take them to the right hand side, I should get my reaction terms. Okay, similarly, if I take these three to the right hand side along with F2, I will get my reaction terms. Okay, so reaction from the boundary would be given by these two expressions. Is that okay? Any questions up to this point? Okay, the only thing that now remains in this is that when we are using the penalty approach, how do we find out the reactions? If you remember, in the penalty approach we had equations given as K prime Q prime equal to F prime. If you have a constraint of the type Q1 is equal to A1, K prime was obtained by deleting the first row, sorry, not penalty, elimination. If you are using the method of elimination, if I delete the first row and the first column in the K matrix, I get K prime. Q prime was obtained by deleting the first row, and f prime was also obtained by deleting the first element from there. Okay, and essentially we are having f prime to be equal to f2 minus k21 a1, this is f3 minus k31 a1 and so on, fn minus kn1 a1, this was f prime. Okay, and k prime and q prime were obtained just by deleting the elements. Okay, how do we find the reaction in this case? Okay, so again, if we look at the first equation, if I take my potential energy expression, differentiate that with respect to q1, okay, I will get k11 q1 plus k12 q2 up to k1n qn will be equal to the force at node 1, and the force at this node 1 will be actually the external forces F1 plus the reaction R1. Okay, so from this equation I can directly say R1 will be equal to this whole expression, that is K11 Q1 plus K12 Q2 K1n Qn minus F1. Okay, so this will be the expression for finding out the reaction at node 1. Okay, once I have solved the system of equation, we will know the values of q1, q2 till qn, all the variables will be known, and you can find out the reactions by this expression. Okay, this is in the elimination method. Okay, and for multi-point boundary conditions, elimination method cannot be used. Okay, multi-point boundary conditions can be solved only by the penalty approach. Okay, any questions with respect to either the elimination method or the penalty approach and single point and multi-point boundary conditions? Okay, so no more conditions, no more questions. I will stop now. What we will do is, in the next class we will go on to what are called as quadratic elements. So far we have been having only linear elements, two noded linear elements. We will go on to quadratic shape functions and we will see how they can be solved.